I'd like to show you an example of computing a double integral of a function over a polar rectangle. So in this case we have the polar rectangle we're calling R, and essentially what R is, it's the part of the unit disk that lives in the first quadrant of the xy plane. So in polar coordinates we have angles theta given from theta equals 0 to theta equals pi over 2 up here, the positive y-axis, and we have r values that range from the origin, which is r equals 0, and since it's the unit disk, it ranges out to r equals 1 for any given value of theta. Okay, so that's what we have here. So we have theta ranges from 0 to pi over 2, and then r ranges from 0 to 1. Now the function that we're integrating, f, it's defined on all of R2, but it is defined on R inside of R2. And it's f of xy equals 2xy. So we've written R in terms of polar coordinates. We need to write our function f in terms of polar coordinates. And to do that, we use the standard coordinate changes x equals r cosine theta and y equals r sine theta. And then we can say f of r theta is equal to 2 times r cosine theta times r sine theta. It's as simple as that. We just substitute x and y for the various functions of r and theta. Now the last consideration is that what we've seen is that dA, written in terms of dr and d theta, is r times dr d theta. And so we've written our differential, we've written our region R, and we've written our function f, all in terms of polar coordinates, so now we're ready to get started. So we're going to write this in terms of an integrated integral, and so the function I have is 2r squared cosine theta sine theta times r dr d theta. And our bounds, so we're doing our r bounds first, we're from 0 to 1, and then our theta bounds, which were from 0 to pi over 2. And so here we go. Now we've written this double integral in terms of the polar coordinates r and theta, and now we can just do calculus. Like, the fact that it's r and theta doesn't even matter anymore. It could be x's and y's. There's going to be no difference from here on out. That this, the fact that r and theta have something to do with polar coordinates is really at this point accounted for, and now we can basically ignore. So since we have a product of a functions of r and functions of theta, we can split that up. So this would be the integral from 0 to 1 of r cubed dr, and then times the integral from 0 to pi over 2 of 2 cosine theta sine theta d theta. Now here it's worth noting that this product of functions, we could use u substitution here. I would let u equal sine theta, but instead I can remember that this function 2 cosine theta sine theta is actually equal to the function sine of 2 theta. This is just the double angle formula from trig. Okay, so I'm going to take the antiderivative of this function instead. So first let's handle the r. So we have r to the 4th over 4 evaluated from 0 to 1. And then here we have negative cosine of 2 theta over 2 evaluated from 0 to pi over 2. Okay, so this sort of this trig identity that we use allowed me to find the antiderivative more easily. Okay, so now we evaluate, and here we get 1/4 minus 0 is 1/4. And then here we're going to do this trick that I like to do, that this minus sign can be accounted for by switching the bounds. So what I'm going to do is get rid of the minus sign by evaluating at 0 first. So I get cosine of 2 times 0 is 0, and then evaluating at pi over 2 seconds. So when I plug in pi over 2, I get pi right here. So I get minus cosine of pi. So instead of evaluating pi over 2 and then 0 and leaving the minus sign, I reverse that. That's a great way to get rid of minus signs without having to write out a couple different steps. So I have this 1/4, and then cosine of 0 is equal to 1, and cosine of pi is equal to -1. So 1 minus a -1 is +2. So this is times 2. And then I guess I had a 1/2 here that I forgot about. So let me throw that in there, and that makes this 2/2. And so in the end I just get 1/4. Okay, so there we go. We've computed the double integral of our function f of xy equals 2xy dA over this region R, which is a quarter of the unit disk that's in the first quadrant, and what we computed it to be was 1/4.